This is Saxon Advanced Math, Lesson 105, and this is dealing with cofactors. Now we'll go into this very quickly, and I think you'll understand this is just a shortcut method for finding out determinants. And let's take it first of all. If we looked at elimination and we said this is a trinomial, right, equal to a constant. So it's a k, and it's x, y, z, and the a, b, and c are the coefficients. So you have a1, b1, c1, and these are the coefficients a2, b2, c2, and so on. Notice that the x's don't have any other subscripts because this is the same x, all the same y, and same z throughout, although the constant does have different constants. Those are different. Okay, if I solve this with elimination, and we didn't take the time to do this, but we did this before. If I solve this elimination, I end up with this here, right? And this, if you want to look back at the where we introduced the matrices and determinants, you'll see that this is how we solved that. And with Kramers' rule, when we were solving or explaining Kramers' rule, with Kramers' rule, we would get this, and we would say, oh, hey, this constant value here gets put in here in the place of the a's, and that would be b and c, and so we're crossing out the constant. Now, we've already developed this as a determinant method for the Kramers' rule. However, if we do the same idea, we're really saying that this is Kramers' rule, right? A1, B2, C3 plus, so you're adding and then subtracting. Now, I showed you where you could show and just distribute this negative, and that's what they did here. They distributed the negative, and if you go back and watch the Kramers' rule video if you need to, I understand that, you'll see where this came in play. Now, once you've done this, if you rearrange the terms so that all the A1s are first, so there's A1, and there's your A2, A2, and then A3, A3. And that's all they've done is put them in a different order. If they factored out the A1 from the first one, the A2 from the second one, and the A3 from the third pair, I would end up with this, which I could say this is exactly the same thing as the matrix. Notice this is a matrix here, minus, right? This one times this one, minus this one times this one times this one, minus this one times this one, and here this one here times this one here. That's the same thing. So if we go back to the original determinant, we could say that they're labeling these. I could say there's my original determinant, A1, B1, C1, A2, B2, right? And I just crossed those out. I would say for A, I would get just this portion, right? That's the same as this. For B, I would cross out the B, right? The B portion, and I would get just this for A2. For the C, for the next one here, for A3, I would say, well, hey, that's B1 and C2. Well, look at this. It's in the upper corner of the same thing. I'm crossing out that line, right? So I'm crossing out the A line each time, but for crossing out the first one, then the second one, and then the third one. And it gives me these three determinants, okay? We get M, right, from Q by crossing out the row of A1, N from R by crossing out the row from A2, and P from S by crossing out the column further, right? And so we can further see the original development of this method required no great insight, but did require persistence and patience, and they're saying, yeah, and certain fascination with looking at the patterns. Whoever figured this out, first of all, was playing with a lot of numbers to figure out, hey, wait a minute, it's the same thing, okay? And then they did a lot of trial and error. The advantage of this, why do we care, is that we can use this to find the determinants of a square matrix of any size by breaking them down to expressions which contain smaller square matrices, which also can be broken down, and we keep breaking it down further, right? When we cross out the row and column of an entry, we call the smaller determinant the minor. Now, they're going to use that term later, so pay attention to it, of the entry. But if the proper sign is applied, appended to the minor, then the combination is called a cofactor. And that's where these cofactors are going to come from. As we saw above, not all cofactor signs are positive. Notice that some of these cofactor signs are not positive, right? We had the negatives in here. So we can show this, therefore, by looking at this pattern. And this is they didn't take the time to show this, but if you look at it, it does this. Plus, minus, plus, minus. So it just starts, and if you notice, it just flips. And so there's never a duplicate sitting next to each other. That's how you can reset this matrix. See, this matrix, if you wanted to recreate this by just saying it goes, and it's square, so it's going to work out every single time. Okay. Now look at example 105. We'll do this together, and you'll see where this comes in play. Find the cofactor of 7. So we're finding this one here. Now you're going to like this because this is really nice. All I'm going to do is take the 7, cross this line out, and cross this line out, because those both are in 7. It's the column that 7 is in and the row that it's in. Now they've crossed those out for us. The minor element, okay, is going to be 2, 2, 6, 5. Okay? But I need to know which one of these is negative and positive. And so because of this, I would have said that goes positive, negative, positive, negative, positive, right? Because it's a square matrix. So it has to go back and forth. So for 7, it's going to be a negative. So the negative minor is going to be 2, 2, 6, 5, and that would be the cofactor.